Today we're going to pick up with the ANOVA F test, which is a test of inference for simple linear regression. Remember, ANOVA stands for Analysis of Variance. We're able to see where all the sources of variation in the simple linear regression line come from when you build the ANOVA table. So remember, we're testing the null hypothesis that the slope is 0. And we're going to use information from our table, MSM, which is mean square model, and MSE, which is mean square error. So the F statistic is calculated using this format. It's a simple ratio. This is on your formula card if you need to go back and check for it. When you run the test of inference or the F statistic, we're going to put this into our iPad. But to provide enough evidence against the null, because it's simple linear regression, the model only has 1 degree of freedom. So the iPad is going to ask you to put degrees of freedom in for the numerator. And then it will ask you for degrees of freedom for the denominator. And that's always n minus 2. So observation minus 2. What we're calculating is the ANOVA F statistic. In Chapter 7, we did skip this. The F statistic for equality was a way to tell if standard deviations or variances were equal. We're not going to worry about that, but I just don't want you to confuse it. So we're running an ANOVA F statistic. When you set up the hypothesis for your inference test, obviously we need an alternative. So typically we run a two-sided test here and we say the slope is not 0. Again, this is the ratio to calculate the F statistic. The F distribution is a highly skewed distribution. When we calculate our F statistic, we're looking to see how far in the upper right-hand side of the tail we actually are. The further to the right, the more evidence against the null you're going to have. Remember, with simple linear regression, what we're actually looking at is a t-test. In a future example, if you have the values of the t-test, you can square that value and also obtain the same value for the F statistic. So they are highly related. So this table we looked at yesterday a little bit. What you're seeing on the left-hand side are the different sources of error. The sum of the squares tells me the value of each of those sources. They can be calculated by hand, but we typically do not. We either let Minitab or the calculator do it for us. We have our degrees of freedom. Most oftentimes, we'll have to calculate the mean square. So we have mean square for the model, MSM, and mean square error, MSE. Remember on the previous slide, we said if you take MSE and square root it, you'll have the standard deviation. And then the F statistic is the ratio of MSM to MSE. The p-value will be calculated on our iPad, and we'll go through that in a little bit. So again, we don't know the standard deviation. So typically this would be a t-test. But we could look at the residuals, figure out what the values of all the sources of error are. It's pretty tedious. This is the formula right here. Ultimately, what it comes down to is I need to know what MSE is. And when you build the ANOVA table, we can usually calculate MSE pretty simply. So our standard deviation, S, for the sample is going to be our unbiased estimator because we don't really know what standard deviation is. And then again, down here, to calculate that, it's the square root of MSE. We'll really need this part moving forward. So let's try our first example. We have a data set called Healthy Breakfast, and it says that it does have other variables, but we're interested in the number of grams of sugar in each serving. They have a sample size of 77 cereals. They're saying sugars is the explanatory variable and rating is our response variable. And they've provided a linear regression equation to calculate and make a predicted rating value. The values provided in the partially complete table are random. There's nothing special about them. At different times, they'll provide other pieces of information. It's just that we can fill in what's missing. So starting with regression, the degrees of freedom, since it's a simple linear regression and there's one explanatory variable, degrees of freedom for regression will be 1. Even though they provided error as 75 degrees of freedom, remember this is n minus 2, so we had 77 observations, minus 2 would provide the 75, and then the grand total is obviously 76. Moving on to sum of squares, we're looking for the sum of the squares error. This is a simple subtraction calculation. I know the total. I know the sum of the squares for the model or the regression, so I'm just going to subtract and obtain that value. To calculate the mean square for the model, we're simply going to take the sum of the squares and divide by degrees of freedom. We're going to do the same for the mean square error, MSE. So we'll divide by degrees of freedom. And now that we know both of these values, we can calculate our F statistic. We set it up as a ratio. 102 is considerably large. When I calculate the p-value, I am going to use my iPad. Down here in the bottom left, I put the keystrokes in. So just like you would obtain any distribution like the norm CDF or T-CDF, if you scroll down the list, you'll find F-CDF. 0 is my lower bound. It's always 0. This distribution doesn't go beyond 0. Your upper bound is your F statistic. We have 1 degree of freedom in the numerator, 75 degrees of freedom in the denominator. And when I enter all this, it returns a value of 1. But since I'm in the upper right-hand tail, I do want to subtract so you can see my p-value is 0. If you're unsure about how I calculated any of these, obviously you can stop the video and go back and go through the explanation. But we are going to try another example. So if you want to pause the video and read this information, I'm also going to ask you to take a minute and enter all this data into your iPad so that we can move forward with our calculations. They have provided a partially filled in coefficient table for our white spruce trees. You're able to completely fill in the coefficient table. This is different than the ANOVA table. The coefficient table allows you to write the regression equation and obtain all the coefficients associated with each of the different pieces of your regression. So if you want to take a minute, we're going to go into stat tests. This is not stat calculations. And then you want to look for linear regression t-test. It's going to ask you to designate an X list and a Y list. You'll also see that they have provided the alternative hypothesis for you. So once you hit enter, our regression analysis is comparing height versus diameter. The constant is our y-intercept. We don't typically run any kind of inference test on our constant, but if you look at the iPad results, we are looking for our A value. A on regression represents our intercept, and the value should be 9.14 and some change. They did provide the standard error for the constant, and the t calculation would be coefficient divided by standard error of the coefficient. So we could have calculated t ourselves. Continuing on with the iPad, the diameter, the coefficient for that is represented by b, which is my slope. So we have 0.481474. And if you read down a little further, the standard error for the coefficient will be called SE slope on your iPad. And we could calculate the t statistic by hand by dividing coefficient over standard error for the coefficient. But they do provide it up in the data. Again, it says t. And it's also providing the p-value. What I want you to do is I want you to touch the cell that says 2.08926. I don't want you to be tempted to think that the p-value is 2. When you select that cell, it's showing you E, -9. That means that this is scientific notation and the value is so tiny that it is essentially 0. So both of my p-values for the constant and the explanatory variable are 0. We are able to write our regression equation. So to predict the height of a tree, here's our slope. Our explanatory variable is the diameter at breast height, and there's our intercept. Now, we want to look at the sources of variation from that regression line. So the regression represents the model. Remember, one explanatory variable is 1 degree of freedom. For degrees of freedom of error, we had a sample size of 36. We're going to subtract 2, so it's 34. And obviously the total is 35. Now, we need to calculate the sum of the squares for the model. If you were calculating mean square, we would divide. So we're going to do the opposite. We're going to multiply the mean square and the degrees of freedom by 1, which is pretty simple. The sum of the squares for the error was provided, so we can get a total by adding. I also want to calculate the mean square error, so it'll be sum of the squares, 95.7, divided by 34, degrees of freedom for error. And from these two values of the mean squares, we'll calculate our F statistic, which is quite large. At this point, you can put this into your calculator. So again, it's an F CDF. These are the keystrokes, and it does return a value of 1. So essentially, the value of P is 0. If you think back to the last slide when we did our coefficients table, they told us the T value for the variable was 8.0685. If you square that value, you do obtain the F statistic, which we just calculated here. So the t-test and the f-test are highly related. This is the Minitab output for the same calculation we just performed. So you can see in a Minitab output, they have a regression equation. They also provide the coefficients table. These have the slopes and your standard errors, and your t-test results and the p-value. And then they also did an analysis of variance in ANOVA, and we have the same results in our ANOVA that they had. We're just going to let the calculator help us. There is no homework for this particular set of notes. If you have any questions, though, about what you saw in the lesson, please make sure you contact me. Have a great day.